Hello everybody and welcome to Gravitational Fields Lesson 1. Obviously in this topic we're going to be looking at gravitation and all the laws to do with gravitational fields. Now firstly today we are going to be looking at the law that governs the force between two masses. Now these can obviously be two planets, planet and a sun, moon and a planet, but really it will govern the force between any two masses. This law then that we're going to try and derive in this lesson is known as Newton's gravitational law. So obviously named after Isaac Newton, exactly the same as Newton's laws of motion. In fact, in the Principia Mathematica, Newton's gravitational law came directly after the three laws of motion. So what we're going to do then is we're going to imagine that we have two planetary objects. It could be a sun and a planet, it could be two planets, whatever it's going to be. The first one and the bigger one that I've got on here I'm going to label with a capital M for its mass. So capital M is the mass of object 1 and the second one I'm going to label little m. So we're using both big M and little m for mass. I'm also going to label the distance between two, okay, which will be labelled r. So r is the distance. Now at this point we need to think about what that distance is between, and you note that the way I've drawn it has already given you a clue as to what this distance is referring to. In this situation we're looking at the distance between the two centres of mass of the objects. Now realistically in Newton's gravitational law, when Newton first came up with the law, he did actually treat the planets, the data that he had for the planets, he did treat them as point-like objects. Now you will have seen a similar approach to this when we looked at Coulomb's law in electric fields, treating them as point objects. And it was okay for Newton, but just for fullness, just to make sure that we do understand what we're talking about, we are going to take it as the distance between the centres of mass. So now let's have a think about how the force between those two objects of mass depends on the things that we've already flagged up. So we had, just to remind you, the mass of the larger object, large M, big M, mass of the small object, little m, and we had r, which was the distance between the centres of mass. Firstly then, let's think about how the two masses affect the force. Now hopefully it should be relatively obvious that if we increase the mass there will be a bigger force between the objects. So both of those are going to be proportional to the force. So therefore the first thing we can say is that the force is proportional to the product of the masses. Secondly then, what about the distance? Well, just like in other forces, especially when we look at Coulomb's law, we have an inverse square relationship. So F is proportional to 1 over r squared. Now of course at this point, if you've already watched the electric fields topic, you're probably going to be able to start spotting some similarities between how we approached Coulomb's law. In Coulomb's law, we said that the force was proportional to the product of the charges and inversely proportional to the separation of the charges. And funnily enough, when we just change that for masses and look at Newton's gravitational law as opposed to Coulomb's law of electrostatic force, we can see that there are a lot of similarities here. Product of masses and inversely proportional to the square of the separation. So we do just need to say inversely proportional to the square of the separation. Now there is another facet of Newton's gravitational law that we need to make sure that we take into account, and I'm going to say that the force is always negative. Now you might at that point want to think to yourself, well, why is the force always going to be negative? Well, again, go back to some of the basic stuff that we've done on forces, again in the electric fields topic, but also going back to the particle physics topic in year 1 and looking at the strong force. A negative force implies that it is an attractive force. Now we know that gravity is an attractive force. Gravity being an attractive force is what's keeping you rooted to the ground at the moment. If gravity wasn't an attractive force, then we would all be floating up in the air. But whether you're sat on a chair watching this video or stood up, what is keeping either your backside on the chair or your feet on the ground? Well, it's the attractive force of gravity. So therefore we do need to explicitly state that this force will always be negative, and therefore we're saying that it is always attractive. Let's then bring those three things over onto a new slide. So F is proportional to the product of the masses. F is inversely proportional to the square of the separation, so proportional to 1 over r squared, and F is always going to be negative. We can start to combine these into an equation then. So obviously the equation is going to start with F being proportional to, and let's find a way of combining all three of these things together. Well, if we start with a minus sign, then that gives us the third one straight away, that F will always be negative. We need to have over r squared, so that gives us number 2. And then obviously on the top we've got to have the product of the masses, so we've got big M and little m there. So that's all three of those conditions satisfied in that. It's not quite an equation, we've still got the proportional sign in there, but we're at least getting close. Now obviously with the proportional sign we know that we always want to replace that with an equal sign and a constant. So F is equal to, keep the minus sign in, obviously we're going to have some constant in a moment multiplied by m over r squared. Now in this law the constant is known as the universal gravitational constant. It takes the symbol of a capital G, and the value of it is 6.67 times 10 to the minus 11. Now the units for the universal gravitational constant we'll look at in a few moments time. Finally then, when we put G in instead of our generic constant that we've got in there, what we're left with as the final equation is F is equal to minus G big M little m over r squared. If we bring that equation over to a new slide, then we have F is equal to minus G big M little m over r squared. So let's just make sure that we define our terms. F is force, the M's represent the masses of the objects. The R is the separation of the centres of mass of the objects. And G, as we've just said, is the universal gravitational constant, which is 6.67 times 10 to the minus 11. From a units point of view then, force as usual will be measured in newtons, the masses will be measured in kilograms, and the separation will be measured in metres. Now for the universal gravitational constant, if we look at the unit and remembering all of our rules around units that we must have the same on both sides, well firstly we definitely need to have newtons in there because of the force on the left hand side. On the right hand side we need to cancel out the kilograms from the masses and the metre from the separation. So in order to do that first, on the bottom of the equation from the r squared we're going to have therefore metres squared. So on the top we also need metres squared to therefore cancel that out to leave us with just newtons at the end. And then from the masses, well on the top of the equation we've got two sets of kilograms, so the masses will give us kilograms squared, and then in order to cancel that out we therefore need a per kilogram squared to cancel those out and leave us with just newtons. So there you have it, there's the unit for the universal gravitational constant, and that leaves us with overall 6.67 times 10 to the minus 11 Newton metres squared per kilogram squared. Now of course Newton's gravitational law is an example of an inverse square law. If we have a look at the equation again, minus GMM over r squared, it's an inverse square law because we have the distance squared on the bottom of the equation. So therefore F is proportional, as we said a couple of slides ago, to 1 over r squared. If therefore we were to plot a graph of force against distance, we would end up with a graph that looks something like that. Now if we had one distance, let's just say here, we'll call that R1, and we double that distance to 2R1, then probably not quite drawn to scale, in fact definitely not drawn to scale, but if this was F1, then this would end up as F1 over 4. So we've doubled the distance, 1 over the square of 2 gives us 1 over 4 or a quarter, and therefore we've quartered the force. If we were then to move out to 3 times that distance, we would end up with 1 over 3 squared of the force, and we would therefore end up with F1 over 9. So here now is your question for this video. Calculate the gravitational force between A, the Sun and the Earth, and then B, an electron and a proton in a hydrogen atom. Now the one piece of data that I will give you is the radius of a hydrogen atom is 53 picometers. Everything else everything else that you require for these two questions can all be found on the data sheet. Now some of them may not necessarily be obvious straight away, but if you have a look through you will be able to find them all. Obviously as usual, pause the video at this point, go away, work out the answers, and once you've got your answer come back and I'll go through them. So coming back to the answers then, let's do the Sun and the Earth first. So what we need is force is equal to minus G. And then what I'm going to do very quickly is introduce you to a couple of astrophysical symbols. The mass of the Sun, for the Sun we represent a circle with a dot in the middle, and for the mass of the Earth we have a circle with a cross in it. Those are sort of generally accepted. You don't really need to know those for A level, to be honest, but I can introduce them to you anyway. Over the distance squared. Now on the data sheet, well, we'll do gravitational constant first, 6.67 times 10 to the minus 11. Now on the AQA data sheet, the mass of the Sun and the mass of the Earth are on the first page. The mass of the Sun is 1.99 times 10 to the 30 kilograms. The mass of the Earth is 5.97 times 10 to the 24 kilograms. Now for the distance, you may have taken a little bit more searching to find the distance, but what you should find in the data sheet is the definition of 1AU. Now AU stands for astronomical unit, and the astronomical unit is the mean distance, the average distance between the Sun and the Earth, which on the data sheet is given as 1.50 times 10 to the 11 metres. So that is the astronomical unit. The astronomical unit is one of the units that astrophysicists use in order just to make the distances and writing the distances and expressing the distances between planets in the solar system a lot more manageable, rather than dealing obviously with big numbers that go into 10 to the 11, and obviously bigger than that when we get out to the more distant planets. But anyway, coming back to it then, 1.50 times 10 to the 11, and as usual, don't forget to square it. That's one of the biggest mistakes that I see students making, is forgetting to square the distance on the bottom, and obviously in this case it's going to mean that you are a factor of 10 to the 11 out in your final answer. Now what we end up with there, once you plug that into the calculator, is minus, remembering to denote that it is an attractive force, 3.52 times 10 to the 22 newtons. Now that, as we can see, is an extremely big number, but remember again, with the size of the objects we're dealing with, the Sun and the Earth, when you've got masses of 10 to the 30 and 10 to the 24 kilograms, they're big numbers, and obviously over big distances as well. So hopefully it shouldn't surprise you that we end up with a relatively large force between the two planets. Oh, sorry, between the Sun and the Earth, between the star and our planet. For B then, exactly the same. We'll just start to chuck the numbers in. We won't bother writing the equation again. So 6.67 times 10 to the minus 11. The mass of the proton is 1.67 times 10 to the minus 27 kilograms. And the electron is 9.11 times 10 to the minus 31 kilograms, and we divide that by the distance, which is 53 picometers, so 53 times 10 to the minus 12 squared. Now for that one, once you've hit equals, we end up with now a ridiculously small answer. We end up with minus 3.61 times 10 to the minus 47 newtons. Now the reason why I gave you this example is just to show you how small the gravitational force is on that atomic scale. Again, if you go back to the particle physics year 1 topic, we discussed the relative strengths of the forces of the strong force, the electromagnetic, the weak, and gravity on the level that we're dealing with in particle physics. So you can see hopefully now that when we're talking about a force of 10 to the minus 47 newtons for gravity, it shows you really how weak gravity is on that subatomic scale. So to summarise then, in this video we've looked at Newton's gravitational law. Newton's gravitational law says that the force acting between two bodies is proportional to the product of the masses, is inversely proportional to the square of the separation, and thirdly is always attractive. Now, when we combine all of those together with the constant of proportionality as well, we had Newton's gravitational law, which was F is equal to minus G big M little m over R squared, where G is the universal gravitational constant, and was 6.67 times 10 to the minus 11 Newton metre squared per kilogram squared. Now again, Newton's gravitational law falls into the category of inverse square laws. So remember how inverse square laws work. If we double the distance, then we will have 1 over 2 squared of that, so F over 2 squared, which of course means F over 4. If we triple the distance, then we end up with F over 9. If we quadruple the distance, we end up with F over 16, and so on and so on. So that's it for this video. As usual, thanks for watching. I hope you enjoyed that. Please remember to like and subscribe, and I'll see you in the next video.